dot product is a multiplication where you only multiply the parallel components of two vectors to get a scalar number. If the two vectors are exactly parallel, then it would be like a normal multiplication and you would get the full value, but if they're not, you will get something less. So this is the definition of the dot product. Now let's take the two vectors, let's rotate them into the xy plane, which is flat on the paper, if they weren't already, and then let's rotate them so that one of them, in this case the vector A, lies along the x-axis. This is just to make the maths easier. Now we work out the components AX, AY and AZ, and BX, BY and BZ. AX is just the whole length of A, and there is no component of A in the Y or Z directions. B has components in X and Y. Cos theta equals adjacent over hypotenuse, which is bx over b, so bx equals the length of b times cos theta. With the same reasoning, we can see that by equals the length of b sine theta. And there is no component of b in the z direction. So putting these results into the definition equation, the first term becomes the length of a times the length of b times cos theta, and then the next two terms are 0. The fact that we have chosen to do the whole of a times part of b rather than the whole of b times part of a doesn't matter. It would be the same result if we did it the other way around. So you can see that we have multiplied the components which are in the same direction. If the vectors are parallel, theta is 0, cos theta is 1, and the dot product is just the length of a times the length of b, like a normal multiplication. If the vectors are perpendicular, theta is 90, cos theta is 0, and the dot product is 0. This is the opposite way round to the cross product. There you will see that instead of multiplying the components which are in the same direction to find out how parallel the vectors are, we multiply the components which are in the opposite directions to find out how perpendicular the vectors are. So when is the dot product useful? For example, when a force pushes an object, only the component of the force parallel to the movement direction contributes to the work done. So we have the equation work done equals the dot product of force and distance. The cross product is a multiplication where you only multiply the perpendicular components of two vectors to get a vector which is perpendicular to the other two vectors. If the two vectors are at 90 degrees, then you would get a vector perpendicular to both with a length of the full multiplication, but if they're not at 90 degrees, you'll get something less. So this is the definition of the cross product. A way to remember this is that it is the same as the determinant of this matrix. If you want to see why exactly this is the definition, then see the video about why the definitions of dot and cross products are as they are. Now, the same as in the dot product, let's take the two vectors, let's rotate them into the xy plane, which is flat on the paper, if they weren't already, and then let's rotate them so that one of them, in this case vector A, lies along the x-axis. This is just to make the maths easier. Exactly as in the dot product video, we work out the components AX, AY, AZ, and BX, BY, and BZ. Now, putting these results into the definition equation, the only term that doesn't go to 0 is the term AXBY at the bottom, which becomes AB sine theta. And we can see the result is a vector in the z direction, which is coming out of the page and is perpendicular to both vectors A and B and is the size of this parallelogram. To work out which direction the cross product resultant vector goes in, i.e. whether in the positive or negative z direction, you can use the right hand rule. So the first finger along the first vector, second finger along the second, and then your thumb points in the direction of the result. In this case, out of the page. Or you can think of it as screwing in a screw using a screwdriver on the shortest path from A to B, and the screw then goes in the direction of the result. So you can see that we have multiplied the components which are in opposite directions. For the cross product we have done A times by, whereas for the dot product we did A times bx. If the vectors are parallel, theta is 0, sine theta is 0, and the cross product will then be 0. If the vectors are perpendicular, theta is 90, sine theta is 1, and the cross product is a vector with the length of A times b. Because we are doing A times by, we can also think of the cross product as giving us a vector perpendicular to both A and B, with the size of the parallelogram created between them. This is the opposite way round the dot product. So when is the cross product useful? When you are interested in how perpendicular things are. Taking the example of torque, only the component of force, which is perpendicular to the spanner, contributes to the torque. So we have the equation torque is equal to the cross product of the radius and the force. This is slightly confusing as the answer for torque is then a vector pointing out of the page, whereas the spanner moves around in the plane of the paper here. You can think of the torque vector as being the axis the spanner will rotate around in this example.